started. So in the last lecture, you were given some discrete time system, and based on that, you are supposed to comment on how the system will have its impact on the input. So what kind of changes the system will make in the input in order to produce the output. So we were ending with that out of fun we are given different examples. One is identity system, second is zero or constant system, and third is random system. In all these things there is hardly any meaningful relationship between input and output. For identity system, it is identity, so no major relationship. For zero and constant, no relationship. For random, also no relationship. Other than that, if ever there is something, then we can say that the system is working on the input and is choosing something of the input, bringing that at the output, rejecting something at the input, or in other words, is processing the input, shaping the input signal, like that. There can be many words which we can use so that the input signal available has got some properties. There are different ways with which we can look at those properties. Then the system modifies these properties, some properties in some manner, some other properties in some other manner, and so on, and produces the output. So system works on the input so as to produce the output. And looking at the system equation which we had been considering last time, whether you have thought of the system working in what manner? If you look at the relationship between input and output, what will happen? Output would be smoothened. The output is the smoothened version of the input. So it is something said to be like a low pass filter. When we take the average of current and previous few samples, even though it may be previous one sample just, at this juncture it is plain average, it can be weighted average also at a later point of time. Whenever we take the average of current and previous samples, it works as a smoothening thing, as a low pass filter. And the extent of smoothening would be more as you go more and more deep backwards. Only current sample, no smoothening, identity system. Current and previous sample, some kind of smoothening, averaging takes place. So what will happen is that the sharpness of the input would be reduced. Sharpness of the input would be reduced. But at this juncture, I find it is at most necessary to deal with something else. This is because what we are having is we are working with the sampled versions. And the much required thing which would be there sometime this semester or sometime in the next semester for you as a sampling theorem, even though we are not going into its exact details, but its theme would be much important for you, because the entire discussion is based on that theme. And therefore, as a deviation, because to explain the various principles, I thought it necessary to spend some time on that. So as a necessary prerequisite to know the contents in this subject in more details, we have to spend some time on discussing sampling theorem. The reason being, we are switching from continuous systems to discrete systems, and the discrete signal is prepared by only taking some samples of the continuous signal. Have we discussed sampling theorem last year? Do you recollect? No is the very simple answer which is to be given without thinking. And then if you come across that yes we have discussed, then you may say, oh, I had forgotten. So I think I recollect something, but I am not recollecting in which class I had discussed the same things. So we may proceed to some extent. I think in signals and systems also we might have made a mention, but even if it is a repeat, it is not harming you. So I am not much particular about probing whether we have really discussed or not. So signal, as we had stated, is nothing but mapping of one variable with other variable. Mapping of one variable with other variable, and usually the other variable is time. Usually the other variable is time, and we are aware about two-dimensional signals, but at this point of time we may work with only one-dimensional signal. That means we should not mix two complicated things simultaneously. So we have a signal called as xt versus t. We have a signal called as xt versus t, or xt is the signal, and this, to visualize it only, we have a plot like this, equal to 0, and it can be, again, 0 being a relative notion, it can extend on both sides. So xt versus t. Then there are different ways with which we can analyze the signal. xt is a function of time. xt is a function, or rather than we may use xt is alright. ft also we could have used, but we use better. We use ft. So because again xt may get confused with x and all that. So ft is a function of time. Then there are different types of these functions. Number one is it may be a deterministic function. Deterministic function in the sense that we can write a formula. We can express it in terms of a formula wherein in that formula some coefficients come and some either higher degrees or t itself or some other functions like sin t, cos t or e raised to t, something like that. So on one side, on left hand side we have ft is some deterministic function of time. Means ft versus t is a very long mapping, and I can say it's infinite mapping. Why it is infinite mapping? Because for every t from minus infinity to infinity, there is some value of ft. For every t, there is some value of ft, and this infinite mapping can be plotted only graphically. Then, if ever ft happens to be a deterministic function, means that by knowing t, if value of ft can be computed, in that case it is possible to write this ft in the form of a formula. Say ft equal to cos t, ft equal to sin t, ft equal to 0, ft equal to 1, ft equal to t, ft equal to t square, ft equal to root t, ft equal to e raised to minus t. Is it clear? So it is possible to write it in the form of a formula. It is deterministic function. Again, even though we say that ft can exist from minus infinity to infinity, in many practical cases it may be there only for finite time. Means from t1 to t2 only it exists, before t1 and after t2 it is 0. So it is called as time limited signal if t1 t2 are finite, or it is time unlimited signal if we cannot have t1 t2 or t1 t2 are infinite. Is it clear? Then to know ft, how ft can be known? If ft is having a formula, it can be known by knowing the coefficients and some functions in the formula. So for that purpose, there is no need to know it entirely. But if ft is not a deterministic function, it will be a random function, and to know ft, we have to know actual value at all the times. So it is not possible for us to know such function, because what would be the value at t equal to infinity, we cannot know, because it is a priori we cannot know that. So expressing ft as a function of t, there are two ways. One is graphical way and other is analytical way or a formula. In practice, what happens is we may consider some signals for our study, cos t, sin t, like that. But when it comes to actual signal being generated from some sensor, maybe we have a mic. Mic is recording the signal, is converting the pressure signal into a voltage signal, maybe temperature, maybe pressure. Whatever practical signals we do have, for them, it is not possible to fit them into any formula as such. Now, we are supposed to study the theory and apply it in practice. So, as regards to, and when it was with continuous signal processing, that time we were devising some circuits which will try to work in a particular way in order to process the input signal, say amplifier, or good example can be equalizer, bass treble. A good example of analog signal processing or continuous signal processing can be multi-level equalizer or simply bass and treble. Amplifier in general amplifies the speech, whereas bass and treble try to enhance particular feature of the speech, and for that purpose we design the circuits. Then see, we are discussing sampling theorem from its practical point of view. Because I highly discourage classical discussion only because classical discussion is that thing which is taught in a perfect way but not learned by the students. And in a learner-centric approach, the more thrust should be given on the learning part. So, we have to actually very effectively appreciate the initial efforts of those who have thought on these lines. Nyquist was thinking, and what was his thinking? We should have a meaningful discussion rather than just stating sampling theorem without its meaning is of no use. So let us have a speech signal. And the lecture starts from here. Let us say that it is speech signal. And lecture ends at this point. It's a start and it's an end. Now we have with us analog recorder, that is the cassette drive, wherein whatever is talked is completely stored with infinite resolution. Are you getting me? The continuous storage devices are having infinite resolution, even though there may be some issues of accuracy, but except that those are having infinite resolution. Say the conventional camera is said to have infinite resolution, whereas our digital camera is said to have finite resolution. the inaccuracies of infinite resolution are actually so poor, the why digital things are in good practice today, because even though those are having finite resolution, the quantization error is much negligible than the accuracy error of continuous devices. Why digital devices are popular today? They introduce quantization error. The continuous or analog devices are supposed to have infinite resolution, but the issue of accuracy is so important there that the digital devices have much superseded. Now, so when this signal needs to be processed in continuous or analog domain, every value of ft must be taken into consideration, right? In continuous signal processing, every value of ft must be taken into consideration, right? So it includes infinite points, countably infinite points in a finite duration. In a finite duration signal, there are countably infinite points of ft which this processing unit has to consider. So it has to consider entire ft. Entire ft means the signal completely. Is it clear? Then Nyquist was thinking this consideration of all the points, whether I can reduce. Whether I can reduce. We can give some examples. Again, the examples are very much what we can say connected to your life. There was a question of pre-C writing. सारांश लेखन. So in standard 10 there was a question. Write a pre-C of the paragraph given in 1/3 number of words. So a good pre-C writer was reading the entire paragraph and was preparing the pre-Cs by his own mind and writing that. You might have come across, I don't know, or whether you yourself fall part of that there is a class of students. What do? What is asked? We said 1/3. So they take first line, write it as it is, drop 2 lines, then write fourth line. In this way, they complete this. So, the theme of this question is that, again, a very long description which contains some kind of redundancy that can be compressed. If redundancy is not there, it cannot be compressed. And also, the compression should take place in such a manner that the loss should not be significant, is the theme. Similarly, Nyquist was thinking, whatever is conveyed by this signal as a whole, whatever is conveyed by this signal as a whole, can it be conveyed by part of it? Are you getting me? So Nyquist started with this thinking and he was coming to a conclusion that, or he might have worked with trial and error method. in what exact way Nyquist theorem is the part available today, but Nyquist thinking is not available. So it is for us to just guess about the way in which Nyquist might have thought. So what he might have thought, for just simplicity, I remove this r below 0, otherwise it doesn't make any harm, but few may find something odd, so we just keep it. Then the first part which Nyquist tried was, I will not be sending information of all the points, but I will sample. Nyquist was driven by some notion that whatever I am doing, he was confident that it will yield a good result. That all information I will not transmit. I will transmit only few points. It contains infinite points. There are infinite points in this finite length segment. He was thinking that I will transmit only finite points. I will choose some points and I will transmit. Then if few Nyquists are existing in this class, then one will say, yes, I will transmit this information, then this information. Only 3 points I will transmit. Only 3 points. So what is available? Available things is this. This is the height. So based on these 3 points, we just like this is writing by writing one sentence, then dropping to taking one. So by these 3 points, do you get the information? Do not get. Then what can we do? Further divide in 2 parts. At least somewhat more educated. Further divide in 2 parts, further 2 parts, further 2 parts. Is it clear? So by this process, if you find that you will transmit this point, skip between. That means if you decide that out of these infinite points, I will transmit say 1000 points or 1024 points. Why 1024? Because by 2 times we multiply by 2, we go to that. 1024 points. In that case, you by common sense feel that, and then after transmit that. How to transmit is not yet known. But earlier, when all were required to be transmitted, now you transmit only few. So when you transmit the few, how will you reconstruct? You will be having a sample and hold. What will you be having at the other end? At the other end, you receive this. Then after some time you are receiving this. Then what will you do? You will have a circuit which will receive this. This sample it will hold till here. Then it receives this. It will hold till this. Then suppose it receives this. And like this, it will trace it, and again the same can be passed through a low pass filter, so that these edges may be further smooth. It's an analog low pass filter, so these edges would be further smoothened. Then again, by an enough common sense, one can very easily conclude that if I take more samples, the reconstructed waveform, how to reconstruct? Take samples. So you know only samples. You do not have any information about the signal in between the samples. The process of sampling means you take the value of the signal at the sampling instance, and the value of the signal in between two sampling instants is not known to you. So you only transmit the sampled signal at sampling instance and presume that whatever is available at the first sample instant will continue till next sample instant. Then you join them and then pass through a low pass filter so as to remove the edges, discontinuities. Then by common sense, every individual can understand that as I increase the number of samples, I would be going more close to actual signal. Is it clear? Or I think there should not be any ambiguity. As I increase the number of samples, I go more close to actual one. Then whether I will reach the actual one or not can be a matter of study. Is it possible to exactly reach? Means, is it possible that the complete information in the original signal, can it be conveyed by these samples? This answer is very typical answer. It requires some kind of time unlimited signal, the concept of highest frequency contained, the concept of sampling frequency, and all that. That statement is a classical statement. We are aware of the Fourier transform or Fourier series. If we sample the original signal by a sampling rate which is more than what we are talking about right now? If we sample the original signal or continuous time signal at a sampling rate which is more than double the highest frequency component in the signal, then it is possible to completely reconstruct the original waveform from the samples. I again repeat, if we sample the continuous time signal with a sampling rate which is more than double the maximum frequency component in the original signal, then it is possible to construct the original signal back exactly from the samples. So sampling should be more than double frequency, more than double of the maximum frequency. Fs must be more than twice Fm. Fs sampling rate, sampling frequency must be more than double the maximum frequency component. What do you mean by maximum frequency component? What do you mean by maximum frequency component? The Fourier transform, Fourier analysis provides us the concept of maximum frequency component. So this discussion is not so easy that it can be understood immediately, but for such signal, the Fourier transform will be, if we have a time limited signal, its Fourier transform is band unlimited. So there will the maximum frequency component in such signal will be infinity. So it is not possible to exactly sample this signal so as to recover the original signal back. But we can have a practical understanding that we can have its Fourier transform, we will find that after certain frequency the amplitude is highly negligible. So if we ensure that our sampling rate is double than that frequency for which and after which the amplitudes are less than, I don't know whether you recollect Fourier transform or not. If you find its Fourier transform, then you will find that the Fourier transform may be somewhat like this. It's symmetric on both sides. Maybe like this. This negative part you need not see. You see on the other side. But what will happen? It will never reach zero. It will be continuous. Then, for such signals, you have to find a threshold wherein that part after which the area is less than, say, 0.1% of the total area. The area after a particular frequency, area under the curve is less than 0.1% of the total area. If you define this to be maximum frequency component, if you define this to be maximum frequency component and then sample at a rate which is more than twice of this, then you can reconstruct to a fairly appropriate level. So, for all practical purposes, nowadays we are having good ADCs, so sampling is at substantially rapid rate. Sampling is at substantially rapid rate. So, one thing which must be kept very well in mind, that whenever we work with discrete signal, we work on samples. Samples are taken by sampling the original continuous time signal. The sampling rate is much sufficient so that because of sampling we do not lose much information. The idea which must be very much clear is that xt is available. From xt we construct xn by sampling. We process xn. We produce yn. From yn we produce yt. Right? In this entire process, the step of generating xn from xt, so generating xn from xt is not part of digital signal process. So if there is some error there, then there is no purpose of discussing DSP. So the purpose of this lecture is just to make you aware that whenever we generate xn from xt by sampling, we are sampling sufficiently so that we can obtain xt from xn also. Forget about further processing and yn and yt. xt we are sampling to xn. Then the question is whether this transformation is invertible. You get my question? Are you finding inverse of the matrix? We have xt, which is continuous signal. From that we are obtaining xn, which is discrete samples. Which is actually we don't obtain xn also. We don't obtain xn as discrete samples. Why? Because how do we store discrete samples? So we directly obtain digital samples. In theory we may say we obtain discrete samples, but discrete samples can't be stored. We do not have that much mechanism. Right? So xt, which is a continuous signal, from that, for practical purposes, we obtain digital samples, xn. xt is a continuous signal, xn is a digital signal. In theory it's discrete signal, but it can't be stored, so let us be practical. So continuous signal is transformed into a digital signal. My question now is whether this transformation is invertible. Whether this transformation is invertible. It cannot be invertible because in digitization I have lost something, and also in sampling I might have lost something. So it is not completely invertible. This is not completely invertible. Then we go to that kind of transformation which is partially invertible. Have you heard this word ever before? Partially invertible. For invertible we must have one-to-one mapping. For invertible we must have one-to-one mapping. What do we mean by partially invertible? When xt is infinite, xn is finite. Right? So it's infinite to finite mapping. Infinite to finite mapping cannot be invertible as such to that extent. But it is partially invertible in a way wherein what we are having, this is one set we can consider, this is the other set. This is a point in the set Xn. Then we have something here, it is many, it is one. This is many to one mapping. This is many to one mapping. For invertibility, we must have one to one mapping. We have many to one mapping here. We have many to one mapping here. But, so when we have many to one mapping here, when we invert, we reach at its center. So, the reconstructed signal is inaccurate as regards to this region. So this may be means this is transformed to this. When I get back, I go back here only. So this is the inaccuracy. So as regards to partially invertibility, when I take the transform and I take the inverse, I do not get the exact thing. But if the inaccuracy in the retrieval after performing the inverse transform is contained below some level, then I can say that the transformation is partially invertible. Or not partially, we can further say that reasonably invertible or approximately invertible. Are you getting me? The transformation is approximately invertible if the error in retrieving after having an inverse transform is below a tolerable limit. And if I sufficiently sample, or if I sample at a sufficiently higher rate, then I can, and further, if I quantize it with good resolution of say 30 or 64 bits, I can say that continuous signal to digital signal is a reasonably or approximately invertible transformation. So I can get back the original signal to a satisfactory level of accuracy. I may not get exactly, but I get as good as exactly. I can say that this transformation is as good as invertible. As good as invertible means it is not invertible. But to my satisfaction, I can see that it is invertible. Is it clear? So that issue doesn't come. That xt to xn is sample. What are you writing there? So xt to xn is something which is what I can say that when it is as good as invertible, then I can say that working on xn is as good as working on xt. Working on xn is as good as working on xt. Then I produce yn. From yn I produce yt. So it is as good as both these parts, that is the sampling and DAC, and after DAC there is a filter. XT, sampling, analog to digital conversion, storing in array, xn is available to me, computer processes that, produces yn, yn is given sequentially to DAC, DAC produces analog signal, and there is a low pass filter. Why? Because when DAC produces an analog signal, the output of the DAC is that you are giving yn to DAC sequentially. When you are giving it sequentially, you are keeping it constant for some time. So it would be a stepwise. Then the step discontinuities are to be smoothened. So there is one more low pass filter. So XT, sampler, ADC, computer, DAC, low pass filter, YT. Right? So it is as all the things between XT and YT come as a package. We presume that sampling, ADC and DAC and filter, these things are not making much changes, so that we work on xn and produce yn means as good as we are working on xt and producing yt, because these things we are keeping at a sufficiently required level. If sampling rate is not high, in that case it will create its own distortions. Are you getting me? Means the digital signal processing system designed cannot work for any xt and yt. You have provided, means when you design a DSP system, you design a sampler with some sampling rate, then ADC with some resolution, then your actual filter processing algorithm, then output, then DAC, and then filter. It is designed at some sampling rate. So if you apply this system to such a signal for which this sampling is not enough, in that case it may not work appropriately. I will give the example also. Your sampling rate may be 100 kilohertz. Sampling rate 100 kilohertz means what? At how much time you are taking the sample? 100 kilohertz. 1 kilohertz means 1 millisecond. 10 microseconds.